Imagine a machine that defies gravity, lifting itself into the sky, hovering in midair, and responding instantly to commands. That's a drone. But how exactly does it fly? Today, we're taking a deep dive into the physics behind drones, from propellers and lift to flight controllers, sensors, and AI-assisted navigation. At its core, a drone is a flying machine, subject to the same physical laws as airplanes and helicopters. Four main forces govern its flight: lift, weight, thrust, and drag. Lift pushes the drone upward, countering the pull of gravity. Thrust moves it in any direction, while drag resists motion through the air. Understanding how these forces interact is the key to understanding flight. Propellers act like rotating wings, pushing air downward to generate lift. The faster they spin, the more air they displace, and the more lift is produced. Each propeller has to generate enough upward force to counteract the drone's weight. For a 1.5-kilogram drone, each of the four propellers must produce at least 3.675 newtons of lift to hover. The diameter, pitch, and number of blades all affect lift. Doubling the speed of the propeller doesn't just double lift, it quadruples it because lift increases with the square of airflow velocity. Electronic speed controllers fine-tune each motor's speed in real time, allowing precise adjustments for movement, stability, and hovering. A drone hovers because its flight controller constantly balances forces. Tiny adjustments in propeller speed control pitch, roll, and yaw. When the drone tilts forward, the rear propellers spin faster, increasing the lift at the back, while the front slows slightly, creating forward motion. Gyroscopes and accelerometers feed data hundreds of times per second, allowing the flight controller to make instant corrections. This is achieved using a PID control system, proportional, integral, and derivative calculations, which continuously adjusts motor speeds to maintain stability. Without this feedback loop, drones would tumble uncontrollably with the slightest disturbance. Where you place components like batteries, cameras, and sensors affects flight stability. The drone's center of gravity must align with the plane of the propellers. If the center of gravity shifts forward or backward, the drone will tilt, and the flight controller must compensate by adjusting motor speeds. For example, adding a camera weighing 0.3 kilograms 5 centimeters forward shifts the drone's center of gravity by about 1 centimeter. While this may seem small, the flight controller immediately compensates by maintaining level flight. Proper weight distribution ensures efficient lift and longer flight times. The thrust-to-weight ratio is crucial. If the drone produces exactly the same thrust as its weight, it hovers. If the thrust exceeds weight, it can accelerate upwards. For a 1.5-kilogram drone producing 20 newtons of total thrust, the thrust-to-weight ratio is about 1.36, allowing the drone to climb efficiently. This ratio also affects agility, climb rate, and overall maneuverability. By adjusting propeller speeds individually, drones can roll, pitch, yaw, and accelerate in any direction with precision. Even a light breeze can push a drone off course. Flight controllers react in milliseconds, using sensor data to adjust propeller speeds and maintain stability. Torque caused by wind is countered instantly by varying the thrust on opposing motors. In gusty conditions, drones may sway slightly, but high-frequency sensor updates and motor adjustments keep them hovering steadily. This combination of physics and electronics allows drones to maintain precise flight even in challenging conditions. Flight duration is limited by battery capacity and energy consumption. Most consumer drones use lightweight lithium polymer batteries, which provide enough power for 15 to 30 minutes of flight. Power consumption depends on torque and propeller angular velocity. Efficient propeller design, careful weight management, and battery optimization are all crucial for maximizing flight time. Every maneuver, hover, climb, or turn, consumes energy, and the flight controller continuously balances performance with battery life. Modern drones are equipped with GPS, LiDAR, ultrasonic sensors, and cameras. These allow them to navigate autonomously, avoid obstacles, and follow subjects. AI algorithms process sensor data in real time, enabling intelligent flight modes like orbiting a target, automated cinematic shots, or returning home if the battery runs low. These systems work seamlessly with the flight controller, allowing drones to perform complex maneuvers without the pilot needing to micromanage every adjustment. For most hobbyists and professionals, the camera is the main purpose of the drone. Stabilized gimbals remove vibrations and tilt, allowing smooth cinematic footage even during complex maneuvers. High-quality cameras paired with gimbals capture breathtaking aerial shots. The drone's sensors and flight controller ensure the camera remains level, even if the drone tilts, pitches, or rolls during flight. Drone technology is evolving at a staggering pace. Engineers are developing new propulsion systems using tilt rotors and variable pitch propellers to improve speed and efficiency. Swarm technology, inspired by the collective behavior of birds, allows multiple drones to communicate and operate as a single coordinated unit, ideal for search and rescue missions or large-scale mapping. In agriculture, drones equipped with multispectral sensors are already transforming crop management by detecting plant stress and optimizing irrigation. In logistics, prototypes of delivery drones are being tested for faster, cleaner urban transport. And in filmmaking, autonomous camera drones are beginning to understand scenes, framing subjects dynamically without human control. As airspace becomes more crowded, AI-driven traffic management systems are being designed to coordinate thousands of drones safely. In the near future, drones could deliver medical supplies, inspect power lines, assist firefighters, and even serve as personal assistants that capture daily life from the air. New materials like carbon nanotube composites and next-generation batteries promise lighter, longer-flying machines. What began as a hobbyist experiment is now shaping industries and redefining how humans interact with the sky. Drones are more than flying cameras. They're a fusion of physics, design, and artificial intelligence. They represent a future where machines don't just obey commands, but understand their environment and respond intelligently. The sky is no longer the limit, it's just the beginning. This was The Process Inside. If you enjoyed this deep dive, don't forget to like, subscribe, and comment below. Which technology should we uncover next?